I'm going to talk about free body diagrams and how we draw free body diagrams. This will be pretty basic, but the whole key is understanding what forces are acting on an object. Because when we draw a free body diagram, we're trying to show what forces are on there and what direction they're acting. Okay? To do that, we need to understand what kind of forces could be acting. The best way I can think of to make sure you get your free body diagram right is to think of field forces, which are forces that can act across a distance. Think of those first. And most of the time we're talking about gravitation, about the force of gravity, the force due to gravity. Later units we'll be talking about electrostatic forces, the same thing that has to do with static cling, for example. This is also a field force. Things don't have to be touching to be attracted if you have electrostatic force or gravitation. Gravitation, we're going to go into much more detail later on, where it could be two objects attracted together, but for right now, I'm not going to worry about electrostatic. I'm only going to worry about gravitation. It's going to be the only field force that we're worried about, and that is going to be the force of an object being attracted by the Earth. Okay, so we're always talking about a free body diagram for an object, for one object. Okay, so that's a field force, and this is always going to be in, the early units, straight towards the center of the Earth. So gravitation, or the force of gravity, is force straight towards the center of the Earth. Everything else, again, we're not going to worry about that right now. Everything else has to be a contact force, has to be. Okay, so when I throw a ball and the ball's going through the air, while that's in the air, there's no force of the throw, which is this weird, scary thing that people talk about. Oh, the force of the throw is, no. If I am not touching that ball, I am not affecting that ball. I absolutely affected it while I was accelerating forward, but once it left my hand, I am not affecting. I can't do any kind of weird magic to make that thing move. So everything else has to be a contact force. So when we're talking about not the ball anymore, but just a random situation, go have the field force, and for a free body diagram, you represent it, I represent it as a little circle. You could do it as a rectangle or a square. And the force of gravity, I draw it in the direction. We always draw the arrows coming out from this. This represents the object right there. Okay, and so this would be the force of gravity. And we can do a little better than that because we happen to know that the force of gravity, how it's related to the mass, so we can put some stuff in here. We can put numbers in here eventually. Then contact forces. Let's take the case of a block sliding down a ramp. So it's moving in this direction. That's the direction of the velocity. And I go through this list, and I want to look at every possible force. I shouldn't say that. I want to look at, first of all, the field force, gravity, put that on there. Then I want to look at every possible force and see if that can be on there. These are the other forces we've talked about. Well, these are all contact forces. So all I have to do is really say, where is this block in contact with anything? Oh, right there. There is only that surface of the ramp touching the block. So that ramp, that surface, is the only thing that can be putting a force on it. So I look at that, and commonly with surfaces, we have these two forces. The normal force, which is perpendicular to the surface. So there's the surface. Here's the surface right here. So perpendicular and going out would be in that direction. And friction, if it's moving in this direction, friction is parallel and opposite the motion, or the way it would move if it were at rest. So opposite the motion, if it's moving in this direction, friction must be pushing back in that direction. So once I've got those, I can put them on the free body diagram. Normal force is in that direction. And I label it normal force. Sometimes in the future, we might see N. Friction is in that direction. Notice I don't draw it like that, because we always want to draw our forces coming out from the object. That's the convention that we use with free body diagrams. Okay? Now it's moving in this direction. Why is there nothing there? Well, we're going to see later that these three forces combine to accelerate the object maybe down the ramp. Okay? There is no individual true force in that direction. It's what we call the net force if it's accelerating in that direction. So this is the approach I always want you to use. Okay? I want you to draw a dot or a circle. Draw the object as a small circle or block, box. Draw the field forces on it, things that don't have to touch. Okay. Then go around and for each surface, for each contact, draw forces associated with that contact. Draw the forces associated with that contact. So what we did was we had this thing on a ramp, and we said, first thing I did is I drew the object, draw the field force. The only field force, oops, there's no C there, is gravity, force of gravity, always straight down. Then for each contact, draw the force, I should put parentheses, force or forces associated with it. A surface, a thing sliding on a surface is going to feel a normal force and force of friction. And you've got to have them in the correct direction. Okay? Let's do another problem really quickly using this exact same approach. Okay? It's really important to be able to associate the correct direction with each of these forces. Remember, tension is a pulling force along the rope or the string or the wire. Okay, I'll switch colors just for variety's sake. Okay, we've got a, I'm trying to think of what would be a good one. Let's do this. I've got another one of these situations, and I've got a block here, and it's attached to a pulley here, and on the other side of the pulley is a cat. Okay, and the cat has a flea on it right there. So we want to be able to say, what does the free body diagram for that object? That is the object. Notice there are a whole bunch of objects here. There's a ramp, there's a block, there's a pulley, there's a cat. This is the one I want to draw the free body diagram for. I'm drawing free body diagrams for a single object. Okay, so for that object, I start by representing it, and then I go, what's my field force? Oh, gravity. It's going to come up an awful lot. Then I go around it and I find all the contacts. Well, here's one contact. It's a surface. Surfaces commonly have a normal force perpendicular to the surface and pushing out. It's the force that keeps that object from plunging through the surface. If this were made of tissue paper, the object might rip through like that. The normal force pushes out in that direction, perpendicular. Okay, be really careful. If the angle is like this, the normal force is going to be much closer to vertical. If the angle is like that, it's going to be much more horizontal. So be sure you're paying attention to what that is, what that angle looks like. And then friction would be up the ramp. I don't even know that I did that very well. Okay, and then friction would be up the ramp. Oh, I shouldn't say that. I don't know. Is this heavier than the cat? Is the force down the ramp stronger? It might go this way, it might go that way. I don't know. So friction, in this case, I'd have to tell you, which way is it moving? I'm going to say it's moving that way. So the friction would be in the opposite direction, force of friction. Oh, and I wrote force of gravity. That was wrong. Okay. There's another contact point. So I'm going to go all the way around this. There's a surface, there's a contact point. There's a contact point. What could that be? It could be tension. It's a string or a rope or a wire. Okay, so the force of tension is always directly along the string or rope or wire. And that would be my entire free body diagram. There are no other contact points. So I got the field force. This surface has two forces associated with it. This contact here has one force associated. Where's the cat? Why don't I have force of cat somewhere? Because the cat is not contacting the object. The rope is contacting the object. The object can't look around the corner. The object doesn't have eyes. All it knows is getting yanked that way by a rope. It's getting pushed this way by a slanted object, inclined plane we call it, and it's feeling this resistance pushing the other direction of friction, keeping it from moving freely. It feels that rubbing as it goes up there. So that's my entire free body diagram. Why is it so important to do free body diagrams? It's important because we're going to eventually put numbers with these things and we're going to be solving quantitative problems. But the most important thing about this is you can't get those right if you don't start with the right free body diagram. And I see this all the time. This approach, what's the field force? Gravity. Draw that in the correct direction. What are the contact points? What forces are associated with those contact points? If you stick with that, you won't have these weird phantom forces that don't exist, and you won't miss any forces because you will have, honestly, if it's only touching there and there have to be contact forces associated with those 2 points. So you won't miss them that way. And if you screw up a free body diagram, those generally are very early in a problem. So if you mess this up, there's no way to get the right answer. So you want to make sure you take a lot of extra care on the free body diagram. But it's not that bad, right? Draw the object as some kind of symbol, a circle or a square. Do the field force, usually just gravity, usually straight down. Then go with all the contact points and figure out what the forces are associated with those.